Welcome everyone. Let's continue with chapter 28, superposition of waves, standing waves, and we'll be studying the modes of vibration in a closed and an open organ pipe. There are certain musical instruments like flute, whistle, clarinet, in which sound is produced by setting an air column into vibrations. The simplest vibrations of air column occur in cylindrical tubes of uniform length, and these are known as organ pipes. The organ pipe can be open at one end, which is known as a closed organ pipe, and it can be open at both the ends, which is known as an open organ pipe. In a closed organ pipe, the node is formed at the closed end, which is a position of minimum amplitude, and an antinode is produced at the open end. While in an open organ pipe, both the ends are open, so there is an antinode at both the ends, and in the center there is a node. Let's consider a closed organ pipe which is of length L. Now in a closed organ pipe, the primary wave is A sine omega t minus kx, which is traveling in the positive x direction. And as the reflection takes place from a rigid boundary, the equation of the reflected wave will be minus A sine omega t plus kx, which is traveling in the negative x direction. Now by the principle of superposition, we get the equation of the wave as 2a sine kx cos omega t. So the amplitude of the standing wave in the closed organ pipe will be 2a sine kx, where k is 2 pi by lambda. Now the amplitude will be maximum when sine 2 pi L by lambda is 1, where L is the length of the closed organ pipe. So from here we'll get the value of lambda as 4L upon 2m minus 1, where m will start from 1, 2, 3 and so on. Now for the first mode of vibration, lambda L is 4L, where we've taken m as 1. So L is equal to lambda 1 by 4, as you can see in the diagram A. So we've already studied in the previous presentation that the difference between a node and an antinode is lambda by 4. So in a closed organ pipe, we have a node at the closed end and an antinode at the open end. The length for the first mode of vibration comes out as lambda 1 by 4. Now we know n is equal to v upon lambda, so we get n1 as v upon 4L. This is known as the fundamental frequency, fundamental tone, or the first harmonic. In the second mode of vibration, taking m as 2, we get lambda 2 as 4L by 3, and the frequency is 3v upon 4L, which is 3 times n1, that is 3 times the first mode of vibration. This is known as first overtone or third harmonic. The third mode of vibration, taking m as 3, we get lambda 3 as 4L by 5, and the frequency is 5v upon 4L, which is 5 times n1. This is known as second overtone or fifth harmonic. Comparing the ratios, we get n1 is to n2 is to n3 as 1 is to 3 is to 5 and so on. So from here we can clearly see that in a closed organ pipe only the odd harmonics are present. In the diagrams, as you can clearly see, in the first we have a node and an antinode. In the second mode of vibration, we have two nodes and two antinodes, and in the third mode of vibration there are three nodes and three antinodes. Open organ pipe. In an open organ pipe, the reflection takes place from a free boundary. Therefore, the equation of the wave which is traveling in the positive x direction, is a sine omega t minus kx, and that of the reflected wave is a sine omega t plus kx. As we've already studied, the amplitude of the standing wave as per the above solution comes out as 2a cos kx, where k is 2 pi by lambda. Now, if the length of the open organ pipe is L, then cos 2 pi L upon lambda is 1, and we get the value of lambda from here as 2L by M. Now, in the first mode of vibration, M is 1, so we get lambda 1 is 2L and L is equal to lambda 1 by 2. Using the same method as earlier, that Vn is equal to V upon lambda, we get N1 is V upon 2L, which is the fundamental frequency, or the first harmonic. For the second mode of vibration, substituting the value of M as 2, we get lambda 2 as L, and the frequency is V upon L, that is 2 times the fundamental frequency. This is known as first overtone or the second harmonic. For the third vibration mode, let us put M as 3, and we get lambda 3 as 2L by 3, and N3 is 3V upon 2L, which is 3 times N1. Comparing the frequencies, we get N1 is to N2 is to N3 as 1 is to 2 is to 3. So from here we can see that an open organ pipe produces both even and odd harmonics. If you see the diagrammatic representation, which is showing the fundamental first overtone and the second overtone, we see that at the open ends there are antinodes, and in between there are nodes. So for the fundamental frequency, we have 2 antinodes and 1 node. For first overtone, there are 3 antinodes and 2 nodes. Second overtone, there are 4 antinodes and 3 nodes.